Hello and welcome. In this video, we will explore a key result in linear algebra that Hermitian matrices always have real eigenvalues. Hermitian matrices play a crucial role in quantum mechanics, optimization, and various fields of mathematics. Let's dive into the proof step by step, ensuring clarity and understanding along the way. We begin with the eigenvalue equation that is AV equals lambda V. Here, A is the Hermitian matrix, V is an eigenvector, and lambda is the eigenvalue. Our goal is to demonstrate that lambda must be a real number. Next, we take the conjugate transpose of both sides of the equation. The result is that the conjugate transpose of AV equals the conjugate transpose of lambda V. Now, we apply the property of the conjugate transpose. For the left-hand side, this becomes the conjugate transpose of V times the conjugate transpose of A, while on the right-hand side, the scalar lambda becomes its complex conjugate, denoted as the conjugate of lambda times the conjugate transpose of V. At this stage, let's recall that for Hermitian matrices, the conjugate transpose of A is equal to A itself. So, we can replace the conjugate transpose of A with A in our equation. This gives us, the conjugate transpose of V times A equals the conjugate of lambda times the conjugate transpose of V. Moving forward, we multiply both sides of this equation by V. On the left-hand side, we have the conjugate transpose of V times AV, while on the right-hand side, we have the conjugate of lambda times the conjugate transpose of V times V. Notice that from our original eigenvalue equation, AV equals lambda V. Substituting this, the left-hand side becomes the conjugate transpose of V times lambda V. On the right-hand side, we retain the conjugate of lambda times the conjugate transpose of V times V. Simplifying further, we bring lambda out as a scalar. The left-hand side becomes lambda times the conjugate transpose of V times V. Meanwhile, the right-hand side remains the conjugate of lambda times the conjugate transpose of V times V. Here's the key insight. The term the conjugate transpose of V times V is simply a scalar, representing the inner product of V with itself. This scalar is always real and positive since V is a non-zero eigenvector. So, we can safely divide both sides of the equation by this scalar, leaving us with lambda equals the conjugate of lambda. Finally, we arrive at our conclusion, lambda is equal to its own complex conjugate. This means that lambda must be a real number. If you found this video helpful, please like, share, and subscribe for more content on mathematics and data science. Thank you for watching.